All right, so ready for another day of, what class is this? Programming Paradigms. And I guess you had, was everybody able to do the homework okay last night? Submit it with the system, and you prefixed it with your number and all that kind of stuff? Because I haven't collected it yet, but.
That's the one with it was due yesterday?
Yeah. Okay, good deal. And so, any questions about any of the stuff that we've been doing so far? All right, so at the end of class last time, here, let me start up we'll start up the demo. Where's my screen flow? Here we go. Okay, so at the end of the class last time, we had written this quote, which is the quotient. You remember that? And why do we have all these nested if statements? What problem are we solving there?
Negative input.
Yeah, when one of those numbers was negative. So I think the thing that we got to work was, quote, the quotient of, like if we did something like negative 11 and 3, it handled the negative one correctly, the negative values correctly. By checking, so the way the function works, first we check if d is less than 0, and if it is, we negate it, call it again. If n is less than 0, if that's true, we negate the n, and we call it. So we finally know that when we get to the last if, we finally know that both n and d are greater than or equal to 0, right? That's what we know when we finally get to the last if. And that's when we can do our recursive, well, they're all recursive, but that's when we can do the actual computation of the quotient. Because for all invocations from that point on, the values will be positive. The arguments will be not positive, but non-negative. Yeah? And then what we said, we looked briefly at this slide. And here on this slide, we have the form of the condition function, COND. And what COND does is it allows us to not have all those ugly nested ifs. And take a look at what condition takes as an argument. Does everybody see that this parentheses matches this parentheses? So basically what we have is something like this. We have parentheses, COND, and then parentheses, 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 parentheses. And then this closes out this parentheses, this parenthesis. Is everybody with me on this? So now, look, you guys, Scheme is a dialect of what language? Lisp. And what does Lisp stand for? List processing, right? List processing. And what is a list? A list is a pair of parentheses with elements in the list. That's why we have all these parentheses all over the place, is because everything we're dealing with is a list, right? So look, here's the opening parenthesis, and here's the closing parenthesis of this condition. And furthermore, what are the arguments of this condition? We have, it's a list. But what is it a list of? Lists. Do you see what I mean? And each one of these lists has how many parts? Each one of these little sublists has how many parts? 2. Are you with me? Each one of these sublists has 2 parts. A condition and an expression. A condition and an expression. A condition and an expression. Except that the last one, there's a special keyword. The last one could be a what? Else. Okay, so now here's the way and then the expression, right? So look, here's what the condition function does. What do all functions do? This is the functional paradigm. So what do all functions do? It returns a value. So so the question is, of all these, with this condition, what gets returned? Well, what do you suppose gets returned? One of these expressions. Which one? Well, what it does is it does them in order, the exact same way those nested ifs were that we looked at with our quotient function, right? So what it does is, if condition 1 is true, what happens? Well, yeah, it doesn't output it, it returns it, yeah? I mean, output is like on the screen, but are you with me? It returns, okay? So it returns, and then, but if condition 1 is not true, what does it do? It checks condition 2. So this is not like in C++, this is not a switch statement. The switch statement doesn't test. The switch statement goes straight to it. This is not a switch. First it tests condition 1. If that's true, it returns expression 1. And then if it's not true, it tests condition 2. And if condition 2 is true, it returns expression 2. And then it tests condition 3. And if that's true, it returns expression 3. And if none of these, if all of these tests are false, it returns the else part. And you can have as many of these as you want. Yeah.
Is there a way to have it perform the expressions of each condition as true?
No, it's in order.
Okay.
The first one that's true, that's the one that happens. It's in order. Just like the nested if that we just did. Okay, so here's what I would like, here's what we should do. Let's go back. Here, let's go back to Dr. Rackett, and let's rewrite this with the condition, right? So here, let's just start over here. So let's rewrite our quotient function to take care of the possible negative values of its arguments. Only this time we won't use all those ugly nested ifs. So let's define QUOT. All right, so that's our little version of quotient. And here we'll do lambda. And now, how many parameters does the quotient function has? It has 2. All right, so it's n and d. And now, what we would normally do here is we would normally say if. But now instead of saying if, what do we have? We have COND, condition. Now remember, in condition, what we have is we have a list, and then we have a list, and we have a list, and we're going to have another list, right? But now here's the thing. Inside each one of these lists, there's 2 things, right? There is a condition, and then there's an expression that gets returned if that condition is true. Now you remember what the last one was? The last one was, well, no, we won't start with the last one. We'll start with the first one. Okay, so now, and what goes in here, it's always 2 things go in here, right? This and this. See, there's always 2 things that go inside a condition. So, and what goes in here? What goes in here is a Boolean expression. What goes in here is a Boolean expression. And what goes here is what gets returned if that expression is true. So our first test here is going to be less than D0. So less than D0. And if that's true, what gets returned? Well, D is negative, right? So we have to return our function QUOT, but with the same n, but negating D. So it's negate D. Now, does everybody see how that worked? Now, we got to make sure our parentheses are correct. I think we need one more. Oops. Oh. On the other hand, it's the negation of this. Yeah, so we messed up a little bit. So here we have to negate, parentheses, we have to negate
this. All right, now we need one more paren here. Okay, so does everybody see how that worked? Now that I see how it works. Okay, so here we go. Let's do, now what two things go here? Something and something, right? And what goes here is the condition. So now let's check to see if n is less than 0. So this condition will be less than n 0. And what goes here is what gets returned if n is less than 0. Well, what goes here is we have to negate what? The QUOT of, but now it's n that's less than 0, so we have to negate the n, right? So negate n, and then we return the d, right? And this paren closes that out. Did we do that right? Something doesn't look quite right here. N less than 0, quote. See, I'm counting my parentheses here. Less than n 0, quote. Why do my notes say there's one less paren here? All right, well, let's forge ahead. And this is, and now we know, at this point, we know that both n and d are non-negative. So now comes our standard test, which is if n is less than d. So now we have two things here. And this is less than nd. And then what goes here is our recursive call. So what we have to put here is plus 1 and quotient. Now we subtract d from n, right? So this is minus nd for the first argument and d for the second argument. And that's that one. And now, remember the keyword here? Else. So we else, and now what gets returned? Oh, wait. Sorry. Oh, man. This was all messed up. This is 0 because that's kind of like our base case. Right? Else. I should have copied and pasted that. Else plus 1 quotient minus nd, negate nd, and call it with the same d. And now we close out all of our parens. Boom. Okay, let's see if this works. I hope so, because I hate to have to repeat this demo. All right, let's try it. First we'll do it with the easy ones. 11, 3. That seems to work. 11, negative 3. That seems to work. Negative 11, 3. That seems to work. And now, negative 11, negative 3. And that should be positive, yeah? And that works. So we're good. Does everybody understand that?
Let's do another recursive algorithm. Okay? The next one's going to be sum of first. So what do you suppose sum of first will do? If we do sum of first 4, we'll get 10. Now, why will we get 10? And if we do sum of first 5, we'll get 15. So what is sum of first n? Nobody? Yeah, 1 plus 2 plus 3, yeah. The sum of the first however many integers. So sum of first n is going to do what? Return 1 plus 2 plus 3 plus dot 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 plus n. So the sum of first 4 returns 1 plus 2 plus 3 plus 4. 1 plus 2, 3. Is that right? Okay, and then sum of first 5, 1 plus 2 plus 3. Yeah, 5 more. In fact, so what is sum of first 6? I know, but recursively.
6 plus 5.
Oh, no. Not plus 5 plus 4. 6 plus what? Sum of first 5. Are you with me? So what is sum of first n?
Sum of first n minus 1.
Plus, yes, n plus sum of first n minus. So that's our recursive. And then what is our base case?
0.
All right, so is everybody good? Let's do sum of first. Can we do sum of first? All right, here we go.
So let's define sum of first. And how many arguments does it have? So here we have our lambda. Lambda has 1, right? Lambda n. And so now what was our base case? If what? N equals 0? Oops. If equals n 0. So if any, then what is the sum of the first 0 terms, the first 0 numbers? Well, it's obviously 0. Why? Because 0 is the identity element for addition. Yeah, you remember that from your discrete. Okay, otherwise, what is it? Otherwise, we add what? We add sum of, oops, sum of first, we add the sum of the first n minus 1 elements. So this time our argument is minus n1. Okay, so that's the sum of the first n minus 1 elements. Now, and we have to add that. What do we add to that? We add n to that, right? And now we close everything out. Let's run it. And let's see how it looks in practice. Sum of first, what did we look at? 5? 5 plus 4 plus 3 plus 2 plus 1? 15. Sum of first 4. Wish they had a history. Sum of first 4. That's 10, which is what we would expect.
Pretty good, huh? All right, the next one. Let's take a look at num digits. By the way, you guys, I did put the notes and the slides up on for Chapter 2, but you know what? A lot of the times I think I'm going to be kind of a little behind, and I might not put the notes and the slides up before we actually run through this material in class. But even if I do, I don't think you should look at them when we're doing this. I mean, you know, you guys could be cheating, and when I ask you a question, you could look down at the notes and look down at the slides that are going to come up the next minute. You could say, oh, you know. But, you know, that's no way to learn. I think it's better for you if you don't cheat while we're during the lecture. All right. So anyway, here's the num digits function. What do you suppose num digit? Well, obviously that means what? Number of digits. So num digits 59,274 is 5, whereas num digits of 81 is 2. Does everybody see what it does? It counts how many decimal digits there are in an integer. How are we going to do that?
Divide.
1, 2, 3, 4. Divide by what? Yeah, each time we divide by, that's the quotient, right? So each time we divide by 10, if we divide this by 10, what do we get? 59,274, we get what?
5927.
Yeah, 5927. So we keep dividing by 10, and every time we divide by 10, what do we do? That's what? one more
Digit.
digit, yeah, so you see how it works. Okay, so the sum of first n returns the number of digits in n. Okay, so are we ready for this one? Let's go back to our Dr. Racket and see if we can write this one.
Define num digits. How many parameters does it have? 1. Okay. And now, what is our test? What's our base case? When does it have just one digit? If the number is what? Well, it's if it only has one digit, then how big is it? We're going to assume that the digits are all positive here, by the way. We could, test for the negatives, but we'll just assume that they're all positives here. The precondition will be that it's non-negative. So, well, if less than n 10, right? If it's less than 10, that means it's what? 9, 8, 7, 6, 5, 4, 3, 2, or 1. And all those digits, all of those numbers only have one digit. So if that's the case, what do we return? 1. Because each one of those digits, each one of those numbers only has one digit. Otherwise, what do we return? Otherwise, we return 1 plus, okay, so we do plus 1. We return 1 plus however many digits are in the original number, but now divided by 10. Well, you divide by 10 and throw away the remainder, so that's the quotient. So it's 1 plus num digits quotient n 10. Boom, 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 boom. Boom, dee, boom, boom. And then run. Looks like we didn't have any syntax errors. And let's see how many digits are in 59274. Num digits 59274. How many digits are in that sucker? 1, 2, 3, 4, 5. Looks like 5, huh? Ha! How about that? And how about num digits in the number 81? Looks like 2. How about num digits in 0? 1. All right, very good.
So, let's begin then chapter 3. Now the title of chapter 3 is Iteration and Invariants. And the first thing we're going to do is talk about the terminology. The topic in the first part of this chapter is what we're going to call tail recursion. And unfortunately, tail recursion is not part of the title of the chapter, because what our author calls iteration is more commonly called tail recursion. So you're not going to see this phrase tail recursion in the book anywhere, but this is just so common that you just need to know it by that name. The programming technique that we're going to use, we're going to learn a new programming technique that is super relevant and has big theoretical implications to functional programming, in functional programming. And all the people, you guys know how in computing, you have Mac people and Windows people, and they gets kind of religious, and you have oh, this is better. No, this is better. Well, I'm here to tell you that in the computing, especially in the theoretical, computing programming languages community, there is a really big faction. Actually, this will be good background for the functional paradigm. There's a really big faction of people who absolutely swear by functional programming and think that we should do everything should be functional programming, and there have been lots of big debates over the years, over the decades, about functional programming whether whether it should be used in a production environment and all that kind of stuff. And in fact, even in education, there is a big movement to have this be taught to freshmen and have this be the first programming language that you learn. And there are lots of high-powered schools, MIT, Cornell, lots of big-name schools. They went that route. They went down that route, and they still do, because the functional paradigm is mathematically sound. I mean, it's probably one of the language that has the strongest mathematical foundation behind it. It's based on the lambda calculus, Church's lambda calculus, and it has some really sound theoretical aspects to it. And the criticism of functional programming is that it is not efficient. Are you with me? So people in the non-functional programming camp, they criticize the functional paradigm because it's inefficient. Now, why do you suppose it's inefficient? Actually, we've done enough now to be able to understand what would make it inefficient. So what aspects of the functional paradigm that we've done so far do you think makes it inefficient? Yeah.
You have to press shift to do the parentheses.
No, I'm not talking about how inefficient it is to press the key. I'm talking about how inefficient it is, how long it takes the programs to execute. Too many parentheses, I have to press the key. No, I'm talking about the efficiency of the program execution. What do you know about efficiency in the computing that you've done so far in your other classes? What did you learn when you first learned, like, recursion? Yeah. Yeah, the big O's, the big thetas, that's one thing, but yeah.
Loops are more efficient than recursion.
Yes, that's the numero uno big one. He said loops are more efficient than recursion. Now, why is that in general true? Why is it what makes recursion so slow to execute compared to a loop? Yeah.
You have to push another, whatever it's called, in the stack.
Exactly. That's exactly the reason. It's because you've got the runtime stack. To implement recursion, you need a runtime stack. And then when you make a recursive call, there's lots of overhead to that call compared to a loop. And so the problem is all that's, and furthermore, not only do you have to push all that stuff on the runtime stack every time you make a call, and of course when you make a recursive call, it's a call, it's on top of a call, on top of a call, on top of a call. So you have all that memory allocation, and then when you return from the function, it deallocate, deallocate, deallocate. Whereas if you just run a loop, nothing gets allocated on the runtime stack within a loop. And that's one thing, and then what's another one? In pure functional programming, every parameter is called by what? It's called by value. Which means that whenever you put something onto the parameter, what is it making? What is it giving it? A copy of what you're pushing, of what you're passing, rather. Do you see what I mean? And then we actually this came up the other day. What else did we say that pure functional programming does not have? It does not have what? Call by. Yeah, it doesn't have call by reference. But call by reference is really efficient because you're not having to push the copies of the stuff. And especially with list processing, because you're pushing the copies of the lists on the runtime stack for the parameters. So the number one criticism of functional programming is that even though everybody realizes that functional programming is mathematically elegant and sound and has a much more mathematically sound theory behind it than other programming languages, the criticism has always been efficiency. So is everybody, yeah.
Then can you even make a node in Scheme?
Oh yeah, we do. All data structures can be represented in lists.
Okay.
Yeah.
I was just
A
wondering
list.
how to do that without a reference.
Well, yeah.
Okay.
But that's what it's doing internally. Yeah. So here's the thing. What we're going to learn about with tail recursion is a big way that the functional programmers can answer the criticism of efficiency. Because tail recursion is according to them, is the silver bullet by which the efficiency argument is bogus and we can run it just as fast as everybody else. That's their, are you with me? That's the background of this. By the way, I might mention that the way we're going to approach all of these paradigms is we're just going to jump right into the paradigms and we're going to start programming them. And then after we get some experience, all of this stuff that I just talked about is really important, but we're just going to get it as we go. Because I think it's better if we have the context of being able to program in the language with the feature and then show how that feature matches that concept. You see what I'm saying? So this whole thing about efficiency is coming up now because we already know how to do some programming in Scheme. So anyway, that was a side, but that's related to what we're going to learn right now. So what our author calls iteration is more commonly called tail recursion. And here is why tail recursion is so important. It's because a good optimizing compiler can convert a tail recursive program into an iterative one. And as a matter of fact, what it can do is it can turn it into a loop. So when our author talks about iteration, it's what most people call tail recursion. But why does our author call that iteration? Because when we write a tail recursive function in Scheme, what does the compiler, when we click run and it compiles it, what does the compiler do in the behind the scenes? It actually doesn't make that recursive call. It mathematically transforms it into an equivalent loop. And so there's no runtime stack. The whole thing, and then it can run fast. But not all recursive functions are tail recursive. In order for a function, in order to take advantage of that optimization that the compiler can do for us, the function has to be a tail recursive function. In order for that iteration in order for the compiler to bypass the recursive calls and turn it into an iterative loop. Does everybody see? This is why. So this is why we. It's important in the functional programming in the functional programming paradigm to be able to recognize when is a function tail recursive, when is it not, and how to write a tail recursive function. Because if you can write your function to be tail recursive, it's guaranteed to execute really fast because the compiler will optimize that behind the scenes. And do you understand now why he calls it iteration? It's because behind the scenes the compiler turns it into iteration. But this more common phrase is tail recursion. All right, so the first thing we have to do is we have to understand what is tail recursion. And I think it's better for us to start with what is not tail recursion. Okay? And get this. We will learn what is not tail recursion, and then if it's not tail recursion, it's what? It is tail recursion by double negation. Okay? Now check this out. Here's what's not tail recursion. Look what we have here. N factorial equals n times n minus 1 factorial. Now this is everybody understands how this can be translated to a program, Scheme program, right? I didn't show the base case here because the base case doesn't have any recursive call. But when we translated this into the Scheme program, what did this n minus 1 factorial represent in the program? The what? The recursive call. Are you with me? And then after we did that recursive call, what did we have to do? After we did that recursive call, what do we have to do? Right here it says, what do we have to do? Multiply it by n, yeah? So look, here it is, you guys. Are you ready for this? That little part right there. After we make the call, we have to do some more processing before we can return the final result. That little part right there, after the recursive call, having to multiply by n, that's what makes it not tail recursive. Now, is everybody with me on this? Yeah.
Could you have a variable that's outside of this expression and just have it plus get what you have here?
We don't have get. Oh, this is so good. You asked me the other day about a loop, and what do we say? No loop. You asked me the other day about call by reference, and what do we say? No call by. Guess what you just said?
No
Gets. What is the get? What is the most common? One of the most common statements in all of the procedural paradigm, the assignment statement. Have you noticed that we haven't done any assignment statements yet? Have you noticed that we haven't done any variables, declared any variables? And look at all what we've been able to do, all the computation we've been able to do. In pure functional program, no assignment statement. And when you say plus gets, you're saying, if you say n plus gets 1, you're saying n gets n plus 1. But look at what we've been able to do. Think about that. I mean, that just kind of is slipping up on us. We're going to be able to do a whole bunch without any of that. Can you imagine that, that is even possible? So because after the recursive call, additional processing must be done before the value is returned. That's what makes that not tail recursive. Okay, so here's the general idea. There's several big ideas. Okay, what you do is the function calls a helper function once. So now to turn a non-tail recursive function into a tail recursive function, we have a helper function. All right? So those of you who took the data structures course, you remember how we had helper functions in a lot of those projects? Well, we're going to do the same thing here. Okay? And then what happens, though, is the helper function is tail recursive, and it calls itself tail recursively. Do you see what I mean? And then when it gets its result, it returns the result back to the original function. Is everybody with me on that? So that's one feature of what we do here. Okay? And now, typically what happens is the helper function has an extra parameter. Like if the original function has one parameter, the helper function has 2. If the original function has 2, the helper function usually has 3. So we stick on an extra parameter into the helper function. All right? And then what happens is the extra processing is done in the parameters of the helper function. So the helper function has to call itself just with different. The computation is done in the actual parameter list of the helper function instead of outside the function. Do you see what I mean? So it's like it's transferring the work from outside to inside. And then if you do it that way, then the compiler can make a loop out of it. So that's the general idea. So does everybody get those 4 points? The function calls a helper function once. The helper function is tail recursive, and it calls itself. The helper function usually has an extra parameter, and the extra processing is done in the parameters of the helper function. So check this out. We said this is not tail recursion, right? And furthermore, what is this calculating? This is calculating the what? The factorial of one number. So watch this. What we're going to do is we're going to have the helper function, and instead of having one parameter, it's going to have 2 parameters, a and b. And what it's going to do is it's going to compute a times b factorial. Are you with me? It's going to compute a times b factorial. Now tell me, if the helper function is going to compute a times b factorial, what will the original function call it with? No, but the original function has to give the helper function two values. What will it give it in order to get the factorial back that it needs? It will call it with a value of what for a? No? If the helper function computes a times b factorial, but what you want to return is n factorial, how will you call the helper function? Here, if you can just get this before I reveal it. Here, this will be good. If the helper function, look, the helper function is going to have two parameters, a and b, right? And what does this thing compute? What does this compute? What does the helper function compute? What does it say? What does the helper function compute? It computes a times b factorial. But what do we want? What does the original guy want? It wants n factorial. So what will it call it? How will it call it? For what?
For A.
No. No, 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 no. No, 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 no. No. We want, look. Yeah. Look, here we go. Look, here we go. What we want is n factorial to come out, right? Here we're coming in. See, n is coming in. N is coming in. We want n factorial to come out. Now, what this guy puts out is, what comes out of here? What comes out of here is a times b factorial. So what should go in? What should go in for a and b? That was not a good diagram, but. Come on. In order to get the factorial of something out of this, what should you? We want n to come out. We want n factorial to come out. So what should we make a? And what should we make b so that n factorial will come out? No. If we want, I'll keep asking it again. I don't know how to give you another hint.
A times B is N. No.
It's going to compute a times b. You have a function that computes a times b factorial. You have n coming in. How do you call this? What values do you give this function so that you'll get n factorial out of it? Oh, you're going to go, oh. Come on. Come on. What value? Come on.
N minus 1?
No, it's not that hard. You're back. You have something that computes. Suppose I give you a function. Say, hey, this will compute a times b factorial, and you say, well, I just want n factorial. What do you give it to get n factorial out?
1.
You get that 1 and n. Use 1 and n.
Okay.
Yeah. 1 and because why? You give a 1 and you give b n. And if it computes a times b factorial, what will you get out? N factorial. But yeah, it seems true. But that's what the main function will, the original function will call the helper function with 1 for a and n for b. And if the helper function computes a times b factorial, what will you get out? N factorial. Are you with me?
So the 1 becomes the value of factorial in the helper function kind of thing?
Well, but now the point is we can write the helper function tail recursively. So we've see so here we go. So here we go. In fact, that's what here I'll go one more here. The main function calls the helper function with a value of 1 for a and n for b. And what does the and look? And now here's what now we'll end with this. This is really an important concept. And I think you'll get it. I think you're getting it. Can you see why this is tail recursive as opposed to this? This is our tail recursive call. See, our recursive call here was to call this and then have to multiply it by n. But what is a times b factorial? It's a times b minus 1 factorial.
Because a times b is still a parameter of the function you're calling.
Yes, it's going to have two parameters. And what we'll do is, how will we compute a times b factorial? We'll have a base case, and then what will we have? And then what will we do? If it's not the base case, what is a times b factorial equivalent to? It calls itself, but in place of a, we'll have what? A times b, and in place of b, we'll have what? B minus 1 factorial. Sorry, we'll have b minus 1, because it will compute, and then that will return a times b plus b minus 1 factorial. And then it will call itself, and eventually we'll get down, the base case will be when b is 0. And in fact, let's think ahead. When b is 0, what should this return? Sorry, when b is... Yes, when b is 0, oh, that will be the base case. No, wait. Well, it will return when b is 1. No, sorry. B minus 1. When b is, when b is 1, doesn't this work with 0 factorial? Right, so is the base case when b is 1? Because then it's 0 factorial times a times b. So what, oh yes, it is, so the base case is when b is 1. And therefore, and in that base case, what gets returned by the helper function? No, not 1. A. Yeah? Well, the shame of this is that we have a holiday on Monday. It's Labor Day. And so when we come back on Tuesday, we're going to jump right into here. And I hope you've remembered this. Anyway, good deal. See you next time.